Hello everyone, welcome to the third lecture of the fifth module, which is on 3D NAND flash cell. The disclaimers remain the same. We were discussing in the previous modules and the previous lectures about the 2D NAND flash memories. We discussed about the floating gate NAND flash memories. We discussed about the charge trap based flash memories. So, what we discussed was this 2D flash memory or the 2D floating gate flash memory especially has been there since 1987. And it was discovered by Toshiba in 1987 and brought to commercial production. So it has performed well for nearly 2 decades. But what exactly happened that we had to scrap it or we had to shift to 3D NAND flash memories? So the real problem started with incessant scaling of these 2D NAND flash memories. So in order to meet the customer's demand of high density memory within your mobile phones, within your consumer electronic equipments, the flash memories had to be scaled incessantly. They had to be scaled to even technologies beyond 20 nanometers, and that is where the real problem started. So let us first discuss about the effective size of this flash memory cells, and that is not same as the physical size. So how we define this effective cell size or area is that we kind of calculate the total area of memory array, and in that we include physical cell area plus the area of your selectors, of your source line selector, bit line selector, and word line and bit line contacts as well. So this is the effective area of the entire memory area, and then we divide it by the total number of cells, memory cells I would say. These memory cells can be flash cells. So this is how we calculate the effective cell size or area. And for this 2D NAND flash, for this 2D floating gate NAND, this effective cell size comes out to be 5f squared. Now what exactly is this f? F is nothing, but it's called the critical dimension. Critical dimension, or the minimum possible feature which you can draw on your chip using that technology. So it's also called your critical dimension or the minimum feature size. And for technologies below 20 nanometers, it also used to correspond to the gate lengths. So to just give you a feel of this, all of you kind of must have worked with 180 nanometer UMC technology. So there f is not 180. So 180 nanometer is the name of the technology, but the minimum gate length, let me just write that. So if you talk about, let's say, 180 nanometer technology node, so here the name suggests that f is 180, but that's not the case. So here f is corresponding to 120 nanometers, and 120 nanometers is kind of the minimum gate length that you can draw in that kind of a configuration or in that kind of technology node. So this is how your f is different from your technology node name. And beyond 20 nanometers, I mean below 20 nanometers to like 14, 7 or 10, f has got a very f is no more related to your gate length. So what people did is they tried to minimize this critical feature size. They tried to reduce, they tried to place the cells as close to each other as possible. They tried to reduce their cell area. However, there were several problems that occurred because of that. So let me talk about those issues. So let me talk about the issues with 2D FG cell scaling. So the first, and I would say the most important issue, was the instability in the cell operation. So there was this instability in the cell operation. So what exactly is your cell operation? You have to program that cell to to store some value, or you have to erase that cell to remove those electrons. So there was this instability in cell operation, which kind of made it difficult to program and erase, and at the same time identify whether your device is in the program state or it is in the erased state. So how you find out that? So you have a programmed VT, you have a erased VT, and across your array you will have this distribution, which we saw earlier as well. So if somehow the tail of the distribution of the programmed threshold voltage kind of merges with the tail of the distribution of your erased threshold voltage, then that leads to instability in the cell operation. So your programmed threshold voltage distribution and your erased threshold voltage distribution should be as narrow as possible, should be as far away from each other as possible for stable cell operation. However, as you scale down these devices, what happened was, there was this VT widening or the threshold voltage distribution widening. So let me write that. So threshold voltage distribution widening. And there were several factors which were responsible for this. So one of the factors that was responsible for this is called RTM. So let me write that. So as you scale down these devices, your RTN kind of dominates. So what is this RTN? RTN is, random telegraph noise. How exactly it comes into picture? So you have some traps in the oxide. So the oxide traps, or the interface states, if they are present, what they do is they kind of capture and emit electrons of the channel. They capture the electrons of the channel, and they can also emit those electrons back into the channel. And these things, these traps do aperiodically or in an asynchronous fashion. So what happens here is, let me just draw a MOSFET and then explain that to you. So let us say that this is kind of your MOSFET. This is your N plus, this is your gate oxide, this is your gate electrode. So this is your gate electrode, this is your gate oxide. So let us say that there are some traps here in the gate oxide. Let us say there are some traps here in the gate oxide. So if you have an inversion channel, and as you scale down your devices, even the number of electrons in your inversion channel, that kind of reduces, right? So there are only few electrons in the inversion channel. So let me write this. So as you scale down, so if you have incessantly scaled your field effect transistors, this FET can even NAND flash memory can be represented as a FET, and on top of it you have a storage layer in that gate stack, right? So whatever is kind of applicable to FETs, that is also scalable, that is also applicable to your 2D NAND flash cells. So if you have incessantly scaled your FET, then your inversion layer electron density is also low, right? So if that is low, and some of those electrons, this is already low, and if some of these electrons are captured by your traps in the oxide. Here in the flash cells, it would mean tunnel oxide. So the number of electrons in your inversion layer is already low, and if some of them are captured by the traps in the TO, then the effective threshold voltage that you calculate, or the effective threshold voltage, then it will change, right? So what happens is your effective VT changes. How your effective VT changes? So what exactly is your threshold voltage? It's the kind of gate voltage at which your inversion layer charge density is same as your background concentration or the bulk P concentration of the channel. So if some of these electrons are kind of captured by the traps, then the voltage at which effectively your number of electrons becomes equal to your number of the dopant concentration in your underlying substrate, that will be different. So just because of this RTM, the effective threshold voltage changes, And therefore what happens is there's this VTH distribution widening. And the worst part is that as you scale down, your oxide thickness reduces, and as your oxide thickness reduces, the impact of RTN even further gets amplified. So let me write that as well. So what happens is this RTN kind of increases with scaling down of length, width, and even your oxide thickness. Here it corresponds to tunneling oxide, so that's the same thing as like analogy to FETs. And other thing is there that as you are scaling down these devices, you are kind of placing the two floating gate cells as close to each other as possible. So this RTN increases even with the cell spacing reduction between neighboring cells. So this RTN is one of the factors which kind of leads to threshold voltage widening, and there can be a situation where the program threshold voltage distribution and the erased threshold voltage distribution, their tails overlap, and as such you won't be able to figure out whether your device is in the programmed state or it is in the erased state. So that is kind of very, I would say, detrimental for the cell operation. Then apart from that, you already know that the FN stacks or the Fowler-Northern tunneling, that in itself leads to a threshold voltage widening, right? So the FN stacks also introduce your VTH widening. Okay, and the extent of this VTH widening, so let me just write that as well. So the extent of VTH widening, how do you classify it, or how do you quantify it? So any Gaussian distribution, the widening or the spread of it is kind of measured as its sigma value, right? So the sigma of VTH due to Fn is kind of proportional to 1 by coupling capacitance between the floating gate and your control gate. So this has been experimentally found out that it is kind of proportional to this. It's inversely proportional to the capacitance of floating gate to coupling capacitance between floating gate to coupling gate, so to control gate, and which in turn is proportional to 1 by root of WL. So as your width and length has scaled, even your VTH widening due to Fowler-Northern stacks or Fowler-Northern mechanism, that also increases and leads to cell operation instability. Now a very kind of general statement that in your flash cells, if you compare your flash cells with MOSFET, so flash cells have what? A tunneling oxide, then they have a storage layer, and then even if you talk about the charge trap memories, so they have tunneling oxide, then they have a storage layer, and then what they have? They have a blocking oxide. So together, the effective oxide thickness or the oxide thickness of the flash cells is kind of huge. It's close to 15 to 20 nanometers. And in a MOSFET, in a modern MOSFET or FinFET, the oxide thickness, if it is SiO2, then it's close to 1 nanometer. So what happens if your effective oxide thickness or your oxide thickness is huge? And here also let me tell you about the effective oxide thickness. So I have taken this case of SiO2, but nowadays people have moved to high K metal gate. So in high K metal gate, you kind of replace your SiO2 with a high K dielectric such as HFO2. These are known as high K dielectric. Why high K dielectric? Just because their dielectric constant is high. So for SiO2, the dielectric constant is 3.9. For HFO2, it goes from 25 to 27. I mean, it depends on the process, but it is generally in the range of 25 to 27. So why do they replace it? Because the gate tunneling or the back tunneling. So you assume that your MOSFET's input impedance is infinite. That is, there is no gate current. But what happens is, as you scale down, so let me write that as well. So what happens is, you scale down your oxide, gate oxide. There is this direct tunneling and there are some other trap assisted tunneling mechanisms as well. Because of that, what happens is there is a gate current, finite gate current. That kind of reduces your input impedance. And this is very much sensitive to gate oxide thickness. So what people do is they tend to keep physical oxide thickness as high, like 6 nanometers. However, electrically, or the electrical behavior, which is measured by effective oxide thickness, EOT, that kind of remains close to 1 nanometer. So, as I told you that this gate current is kind of proportional to the gate oxide. I mean, it is kind of dependent significantly on the gate oxide thickness, on the physical gate oxide thickness, I would say, because the tunneling barrier is kind of defined by the physical thickness, right? So your tunneling depends on the physical thickness. However, electrically, you can keep the oxide thickness or the gate control close to that level just by using a high-K dielectric. So what exactly is this EOT? So let me define what exactly is EOT first. So EOT can be defined as, the equivalent thickness of it can be defined as the equivalent thickness of SiO2 required to achieve the same level of electrostatics, What do we mean by electrostatics? Same level of gate control with another dielectric, which can be a high-K dielectric. Let's say with a high-K dielectric of a particular given thickness, of a particular physical thickness. So this kind of relates, if you have been given a particular thickness of a high-K, you can convert it to, how many nanometers of SiO2 does this correspond to. So you can directly write an expression for this as well. So EOT is nothing but it's like the physical of the high-K dielectric, which has been given to you, into epsilon Si, which is epsilon SiO2 kind of, divided by epsilon of this high-K. So let's say you want to achieve an effective gate control with 1 nanometer of SiO2 using a HFO2 dielectric. So what will you do? So what we want here is, we want effective gate control corresponding to 1 nanometer SiO2. So our EOT is 1 nanometer. And then we don't know what exactly is the T physical of HFO2 that we require. And this is 3.9, and let's say this is 25. So let's say this is kind of 1 by 6. Approximately it's 1 by 6. So your T physical of HFO2 required to achieve the same level of gate control as 1 nanometer of SiO2 is 6 nanometer. So here what you did, if you replace your gate oxide with HFO2, which is 6 nanometer, electrically the effective amount of gate control that you are getting is corresponding to 1 nanometer of SiO2, which you actually want. However, the physical thickness is 6 nanometers. Therefore, this direct tunneling and all won't come into picture. So this way you will reduce your IG. So that is the main goal behind using this high-K materials in your gate stack. So I digressed a lot. So by discussing these, what I really wanted to kind of convey was the EOT in your flash cells is very high. And this leads to what? This leads to a poor gate control or poor electrostatic integrity. And because of this, what will happen? Your short channel effects and the narrow channel effects, they will be severe in your flash cells. So as you reduce your gate length or as you reduce your channel length in your flash cells, even your short channel effects will be very severe, even more kind of even worse than your usual MOSFET cells. Why? Because your effective oxide thickness is really high here. So your gate control is already very poor. Okay. Also, if you want to reduce the thickness, so if you somehow come up with a plan that, okay, since it's because of a very high EOT, why not just reduce the EOT? Why not reduce the turning oxide thickness to have a better short channel effect? That is, idea is good, but the problem is with this, your stress induced leakage problem, that will increase. So there has to be a trade-off. I mean, scaling is not at all beneficial for these flash cells. Also, since your neighboring cells are placed very close, so let me write that. So your neighboring cells are placed too close. So once they are placed too close, what will happen? There will be parasitic coupling. Parasitic coupling between what? Between floating gates of adjacent cells. And because of this coupling also, your threshold voltage distribution will widen. So let me write that there will be VT widening because of this as well. And because of this, there are phenomena like neighbor cell disturbance, there's crosstalk and all those things which are happening. What is the other issue with scaling? It's also related to retention, right? We discussed that in ultra scale flash cells, like for 20 nanometer gate length, you already have like only 10 electrons in your floating gate, right? So there's a retention issue as well. So what that retention issue means, already there are low number of electrons in floating gate cells, and if somehow some of these electrons leak, so let's say there are only 10 electrons and like 3 of them leak, then you are only left with 33, like you are only left with 67% of electrons which are kind of dictating your threshold voltage. So you will end up somewhat midway between your programmed and erased state. So these things are really making your flash cell sensitive to noise. And apart from that, another issue, which is kind of a common issue for all the devices, is fabrication challenge, or I would say process integration challenge. Process integration or fabrication challenge. So we discussed about this, right? That we need EUV if we want to go beyond this 20 nanometer technology node. That is available as well. But all these efforts, even if you are taking all these efforts to integrate, the floating gate cell, pattern it well below 20 nanometers using EUV, but all these other factors like this VT widening and all. So if the cell itself is not functioning well, if its operation is itself not good when you are scaling it, then what is the use of scaling? You can reduce the area, but its operation also has to remain intact. And because of all these factors like RTN, because of neighboring cell disturbance, because of this FN stats, and because of this poor short channel effect in this, your operation itself is not stable. And if your operation is not stable, there is no point going ahead and scaling this towards the future technology needs. Lecture also we discussed how your gate all around sonar structure kind of improves upon these issues, some of these issues at least. So let us look at what exactly are the advantages that you get when you go for this sonar structure. So first advantage that you get is, since your storage layer is thin, since your storage layer is a dielectric side 3 and 4, which is kind of thin, so what this leads to is the interference and the neighboring cell disturbance issue. This is kind of mitigated. Just because the storage layer is thin and not a thick kind of floating gate. So this is the first advantage. Second advantage, which comes because of this gate all around structure, because of that curvature effect that we discussed, what happens? Your electric field that the tunneling oxide field is increased and the bottom oxide or blocking oxide field is reduced, and because of this, it helps in your program, it helps in improving your program erase behavior. What else can you say about this gate-all-around structure? So if your gate is kind of wrapping your channel, so if your gate wraps around the channel, then what happens? You have gate control from all the directions. And what about 2D flash cells, 2D floating gate cells? So in 2D cells, you have gate control from only one direction. And that direction is kind of top, right? However, in your gate-all-around structure, the gate wraps around the channel, and you can have this gate control from all directions. So if you have a better gate control, what that leads to? So better gate control improves your electrostatic integrity and diminishes short channel effects and narrow channel effects. So this is kind of helpful even from this perspective. Okay, what else? Another important point is, for these devices, I mean for this gate-all-around structure, since the channel is vertical, so because of vertical channel, what happens is lithography is no more the constraint. How? Since it's vertical, so it's like this. So you have a cylinder going like this. You have a cylinder going like this, and you have gates like this in the vertical direction. So this is your channel, which is going in the vertical direction, and you have gates which are going in the horizontal direction. Gates, or I would say the vert lines, whatever you call it. So here these gates are not kind of defined by lithography, but they are defined by what is called as deposition, right? So you are vertically depositing these gates. So you are defining your gates via deposition. And if you remember from the course on device fabrication, so with deposition, with the advanced tools that you have for deposition like atomic layer deposition and all, you can get angstrom level control. However, even with EUV and all, in lithography, the control that you have is of the level of nanometers. So since the critical feature here, that is the gate length, is defined by deposition rather than lithography, this is also relatively easier to fabricate, I would say, and less process dependent. And since you are kind of integrating several cells on top of each other in your gate-all-around kind of 3D NAND flash memory, so also you have a better area efficiency. How? So remember, if you stack them on top of each other, if you stack different cells on top of each other, your effective feature size becomes f by n, where f is kind of, it becomes like 4f square by n, if you remember correctly, where n is the number of layers of that kind of stacking. So also it's area efficient. So these kind of features make your gate-all-around Sonos kind of vertical channel devices more attractive as compared to your 2D NAND flash memories. With this kind of discussion about the gate-all-around Sonos, especially in a vertical channel configuration, and about its novel attributes and all, let us go ahead and see how we can kind of realize this 3D vertical channel NAND and let us look at this into details. So, there are several ways in which, you can stack NAND flash together, NAND flash cells together. So there are basically three approaches which are most common. So there are basically these three approaches which are most common. So let me just write it. There are these three approaches. And these approaches dictate three things. What are those things? So they dictate the cost, they dictate the electrical performance, or let me just write the performance. And they also dictate what is the process complexity, right? So how you kind of arrange your cells, that kind of dictates all these three, even your 3D kind of integration. So what are the three approaches which people have generally utilized? So the first approach is horizontal channel and gate. Horizontal channel and horizontal gate. What was that configuration? You remember in the last lecture we kind of discussed about integrating the 2D flash cells one on top of each other. So that was horizontal gate and horizontal channel, something like this. Now the second approach, which I discussed in the last slide, that was vertical channel and horizontal gate. So how do you realize this? You just rotate it by 90 degrees, and then you rotate it around this axis like 360 degrees, and then you realize something which is having a vertical channel and a kind of gate all around horizontal gate. This is the most common approach, I would say, and this is what people call VC NAND, vertical channel NAND. There is yet another approach which kind of Macronix and Samsung came up with, and that is horizontal channel and vertical gate. So this horizontal channel and vertical gate, here your gate is vertical and it's a twin gate or double gate structure. Just write it down. So it's a twin or a double gate structure. It's a twin or a double gate structure, unlike the gate all around structure of a vertical channel. So what were the most common cell structures which use this VC? So the most common cell structures which use this vertical channel were this BICS, or what it is. So it's called bit cost scalable cell, or BICS. So this was kind of this is the big structure, and it came from Toshiba. So let me write that as well. So it came from Toshiba in 2007. And Toshiba, it was pioneer. If you look at first 3D NAND flash, Toshiba. First 2D NAND flash, Toshiba. So it was kind of pioneer. It's still pioneer in memory technology. Samsung is, I would say, the most kind of the nearest rival. So Samsung also started its journey towards this 3D NAND flash in 2007. However, it was delayed by 2 years. So in 2008, it came with something which is this structure, which is known as VRAC. So VRAC Samsung came up with in 2008. Then it kind of modified its VRAC structure. It also came up with something which is called ZVRAC. Then again, it also came up with something which is called VSAC. That was also in 2008. So Samsung also kind of, just to give, what should I say, just to give competition to Toshiba, it also started investing hugely on the 3D NAND flash structures, and it came up with these three versions which were unsuccessful. They were not put into commercial production, but most of the people study about the success. But if you want to do something deep, then you should study about these failures. So I would like you guys to know about this VRAC, ZVRAC, and VSAC, and that I would give in assignment. Because if you know about this journey of Samsung from VRAC to ZVRAC, from VSAC, and then to TCAT, which is shown here. So this is TCAT. And this Samsung came up with in 2009. And this forms the basis for all the 3D NAND flash memory from Samsung after this, like VNAND, ZNAND, and whatever you are getting from Samsung, it's all based on this TCAD. And this TCAD kind of, mitigates all the deficiencies of this big structure. So, it's also very important to know about the failures, because unless you know about failures, you won't be successful. So that we'll do in, the assignment part. And what is the full form of TCAD? So the full form of TCAD is, let me write the full form of TCAD. It's terabit cell array transistor. That is it. Let's take these 3D NAND flash memories, I mean the 3D vertical channel NAND flash memories such as BICS, TCAD and all, case by case, and try to understand their operation, their structure and all those things. So first, let us go through the BICS structure. So the BICS structure looks something like this. So let me just write something. So there are these pillars. Then there are these control gates. And they are not control gates, but they're kind of control gate plates. So these are metal plates which are kind of going through all these pillars. And then you have these different bitline selectors. So this is bitline selector 1. This is, bitline selector 2. This is, the bitline selector 3. So you see the control gates. So let me just write it. So there are several pillars. Each of those pillars is a string. So each of the pillars are strings. Then there are these control gate plates which go through several strings, right? Which go through several strings, and the intersection between the pillar and this control gate plate, what that represents? That represents a cell, a memory cell. Okay, and then there are these bitline selectors and source line selectors. So again, if you see, the source line selector is also a common plate. So source line selector is also a common plate going to all strings or all the pillars. So how you can uniquely kind of select one particular pillar? You only have this bitline selector. So how you kind of select one pillar? You kind of select one bitline select. Let us say you select one bitline select here. So you kind of select all these pillars. Then these are your bitlines. So what you do is, then you apply bitline 0 volts on all others, and you only apply the bitline voltage on the particular string that you want to read. So for reading, what you do is, you first select only this bitline select. So if you do that, you select you kind of turn on all of these strings. Then, depending upon what bitline you are choosing, you can select a particular pillar or a particular string. So this is how you read these or address one particular pillar. And again, if you are kind of addressing one particular string, then if you want to address one particular cell of that string, what you do? You kind of put that cell or put that word line or put that CG to some particular voltage, and to all the other CGs, you apply a VPass. So yeah, this is somewhat difficult to grasp. So let me just write them first and then I'll explain it again. So you have this bitline selector through which you uniquely select a particular string, right? And then if you look at, like if you compare this schematic, so you'll see that you have independent bitline selectors, right? You have a bitline, so this bitline is kind of, connecting. So this is kind of, this schematic is a figure in this direction. Like it's kind of a figure in this direction. So you have these pillars, you have these different pillars, which are like this. Wherever there is an intersection between pillar and the control gate, you have cells. So these are cells. Then you have a common source line. You have a common source select line as well. So you have this common source select line, which is here. And then you have a common source line. So what is so special about this common source line? So this common source line is made of N plus diffusion. So you have this silicon substrate at the bottom. You kind of doped it N plus with the help of diffusion or any other process. And then that is how you kind of reduced its resistance. And that is how you realized a common source line. So you kind of doped it N plus to reduce resistance and realize electrical contact or ohmic contact. So I have a common source line. You have a source line plate which is going through all of these kind of, I would say, strings. And then you have these control gates, and at the intersection of each of these pillars with this control gate, you have cells. So this cell, this cell, this cell, these are represented like this. And at the same time, you have these bitline selectors. So this is BLS3, this is BLS2, this is kind of whatever was here was kind of BLS1. So you have these unique BLS. So you have these unique BLS. And all these pillars are kind of connected using one bit line itself. So there is one bit line which is kind of connecting all these pillars or all these strings. And just by turning on or off these bitline selectors, you can select one particular string. And now once you have selected a particular string, then if you want to select a particular cell, what you do? You kind of apply some VG here to that particular cell. And then you apply VPass to all the other cells. And you also turn on, your SLs, because unless your SLs is turned on, like your source line selector is turned on, you won't be able to sync any currents with the string. This is how you can uniquely select one particular cell. Okay, so with this discussion, let me just talk about, talk further more about this. So as I talked already, so this bottom is an N plus diffusion layer. However, even no matter how much you dope it, your N plus layer will always give a very high series resistance as compared to metals. That is kind of one disadvantage, I would say, of having an N plus diffusion layer as a common source line. Here for the pillars or for the cells, they don't use single crystalline silicon. Instead, like in your 2D NAND flash cells, what you used was a single crystalline silicon. It was close to MOSFET, but you only replaced, you only placed your floating gate or a nitride storage there in your gate stack. But here, they don't use single crystalline silicon. Instead, they use what is known as polysilicon. And what is the reason behind that? So the reason behind that is we don't require great transistor properties. Like you don't need a very high mobility. industry is more interested in this? Reducing cost. So use of polysilicon reduces the cost significantly. And since here you are not very much interested in transistor action, here you are more interested in looking at the threshold voltage variation, right? So that you can get even with polysilicon. The only disadvantage is since the mobility is not that high, the current through the string would be very low. And also along with this polysilicon comes the grain boundaries and the traps of the grain boundaries which lead to variability. So we'll discuss that as well. But before going to that, so what are the reasons for which they kind of go for this polysilicon instead of silicon? And another part is they don't even dope it. So they use undoped polysilicon, which kind of further leads to a reduction in the mobility. But why these things are being used? Why they use undoped polysilicon? Why polysilicon instead of silicon? First is the cost. Second is thermal budget. So typically, how these things are made is they kind of deposit these different control gate layers and the insulator layers, and then they etch holes, and then they deposit these things. They deposit polysilicon, they deposit ONO layer. So they have to deposit the channel through deep trenches or deep holes with high aspect ratio. So if they have to do it with silicon, it will require very high temperature. But polysilicon using CVD can flow very easily. So thermal budget also is something which kind of restricts the use of silicon, single crystalline silicon. And also, if you have to deposit it within a deep hole with a very high aspect ratio, then you have to choose a process, a deposition process, which is isotropic, or I would say a non-selective deposition process. So this is kind of very easily available for polysilicon. So that is the reason they use polysilicon. Now the question is, why undope? I mean, you could have doped this polysilicon and kind of somehow improve the mobility as well. But why undope? So there comes this factor which is called random dopant fluctuation. Just to avoid this, they don't dope the channel. They don't dope channel or polysilicon. So what exactly is this random dopant fluctuation? So let us take the case of a MOSFET channel. So the MOSFET dimension is, let's say, the channel dimension or the field dimension is 10 nanometer cross 10 nanometer cross 10 nanometer. It's an ultra scale MOSFET. So you have the dimension as 10 nanometer cross 10 nanometer cross 10 nanometer. Let's say length, width, and height. Now let us say that the channel is doped to a doping concentration of 10 power 18 per centimeter cube, right? This is how you define it, the channel doping. Let's say the channel doping is 10 power 18 per centimeter cube. So how many dopant atoms are there in the channel? So this is your doping concentration per unit volume. So to find the number of dopants, what you do, you just multiply it with the volume. So what is the volume here? Volume is nothing but 10 nanometer whole cube, which turns out to be 10 power minus 18 per centimeter cube. Sorry, it's 10 power minus 18 centimeter. So you just multiply it with 10 power 18 and you get that you only have one dopant atom in the channel. So if you have only one dopant atom in the channel, if your channel is so small, then even location of this dopant atom influences your threshold voltage. So you are doping it with ion implantation process, and your location of dopant atom can be anything. And now because of this location dependent threshold voltage, your threshold voltage distribution will widen across the cells. So that is one of the reasons why they do not dope this polysilicon, just to avoid this random dopant fluctuation. So they avoid this random dopant fluctuation, and that is why they don't kind of dope it. However, with the polysilicon, you have grain boundaries and traps associated with them. So we'll discuss that in the next slide. But another advantage that you have here is you have cylindrical cross-sectional shape. Of the pillar, and you have gate-all-around structure. So, as you remember, gate-all-around sonars with a cylindrical cross-section will have high tunneling oxide field and a low blocking oxide field, and this will aid our program and erase mechanisms. So that way, it's kind of very beneficial. Now, let us talk about the problems that appear when you have this kind of polysilicon as the channel material. So if you have polysilicon as the channel material, so this is your polysilicon as your channel material. So you have these grain boundaries. So what is the difference between a single crystalline silicon and a polysilicon? So in your single crystalline silicon, there are no grain boundaries. In your polysilicon, there are several grain boundaries. And different, let me write grain boundaries as GB. Different grain boundaries have different orientation, right? Crystal orientation. And if they have different crystal orientation, they also have different mobilities. So you have several such grain boundaries across your channel. And also within the grain boundaries, you have traps. So as you can see, these are kind of your grain boundaries, which are represented by these boundaries. And you have traps, which are these dotted lines. So you have grain boundaries and you have different traps associated with those grain boundaries. And because of this, since each grain boundary has a different orientation and mobility, your characteristics or the current will depend on what? On location of this grain boundary, location of grain boundary inside the channel, and also their orientation, right? And the trap density as well. Observe that the number of grain boundaries is proportional to area of the channel. So if somehow you use a thin channel, you reduce the number of grain boundaries in your channel, and as such you also reduce variation due to grain boundaries across different cells. So this is the general idea, and to implement this, what people do is they go for this macaroni body. So they go for this macaroni body. So I guess many of you may have eaten a macaroni. So macaroni is nothing but a pasta which is kind of a hollow cylinder. So let me write. Macaroni is nothing but a hollow cylinder shape. So what these memory engineers did was they kind of edged the hole. So they had this kind of, they had this polysilicon channel. So to reduce its kind of thickness, what they did is they edged a hole, and then let me just write. So what they did was they edged a hole in the channel, and then they deposited a core filler. This core filler is nothing but SiO2, what they use. So using this process, they were able to reduce the channel thickness. Also, if you have a low channel thickness, your electric field lines from gate. They kind of, penetrate the whole channel, and this leads to a very good electrostatic control. So just by introducing this core filler and this macaroni body, they were able to improve first. They were able to reduce the variation due to grain boundaries across different cells. They were able to reduce the number of grain boundaries. At the same time, they were also able to improve the electrostatic control of the channel region. So it was very kind of beneficial one.